Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It's great to be here.
Today, we are exploring what feels like some serious cracks in the code. And more specifically, we're going to be looking at the W boson, the muon, and this really elusive particle called the leptoquark.
It almost sounds like the title of a fantasy novel, doesn't it? The W boson, the muon, and the leptoquark.
It really does, but I think the stakes are just a little bit higher than a whodunit. We're talking about basically the fundamental operating system of the universe.
Yeah.
The source material for our discussion today is, well, it's pretty heavy. We've gone through the latest reports from CERN, some fresh updates from the European Strategy for Particle Physics. This is the new 2026 update, and some incredibly dense theoretical papers on things like scalar leptoquarks.
Oh, they are dense. Absolutely.
Yeah.
But I would argue, and I think a lot of people in the field would agree, that this is probably the most exciting time in high-energy physics in maybe 20 or even 30 years.
Really? Why is that?
Because for such a long time, we've been stuck in this very strange but also very successful rut. We have the standard model.
Right, that's the big chart you see on the wall in every university physics department. It's like the periodic table is much scarier, much bigger brother.
That is the one. And the problem, the central irony, is that the standard model is just too good.
Too good? How can a theory be too good?
Well, it predicts experimental results with, just terrifying accuracy. We calculate something, we measure it, and it matches. But the thing is, we absolutely know it's broken.
Right.
It doesn't include gravity. It has no explanation for dark matter, which makes up most of the matter in the universe. Doesn't explain why neutrinos have mass. So we are certain there has to be something else, something beyond.
But the machine, this standard model, it just kept passing every single test we threw at it for decades.
It did, until recently.
Yeah.
Or maybe it's better to say, until we started looking closer.
And that's the key shift, isn't it? This whole idea of the precision frontier.
That's exactly the phrase. We've sort of moved on from the discovery frontier, just smashing particles together at higher and higher energies to see what new things pop out.
Right, like finding the Higgs boson.
Exactly. We've moved from that to what we call the precision frontier.
Okay, let's pause there for a second because precision frontier sounds a little bit like marketing speak from a lab's PR department. What does that actually mean for you, for the listener?
It's a fair question. Let's try an analogy. Think of it like you're balancing a checkbook.
Okay.
Now, if you're managing, say, $1 billion corporate budget and you're off by a single penny at the end of the year, what do?
I'd ignore it. I'd call it a rounding error and move on with my life.
Exactly. You'd move on. But in fundamental physics, we don't get to do that. If our theory calculates a number, like the mass of a particle, to 8 decimal places, and then the experiment measures it and finds a difference in the 9th decimal place, that 1 penny isn't a mistake.
It's a clue.
It's everything. That penny represents a hidden variable.
A ghost in the machine.
A ghost in the machine. Precisely. That tiny, tiny discrepancy could be the gravitational pull of a new force we've never seen, or the quantum interference of a particle we never knew existed.
So that's where we are. We're not looking for brand new continents anymore. We're mapping the existing coastline down to the millimeter to see if the sand is shifting in a way we don't expect.
A perfect way to put it.
So today we're going to explore 3 of those specific cracks in the coastline. We'll start with the W boson, which had a bit of a midlife crisis a couple of years back. Then we're going to look at the muon, which is apparently wobbling in a way it shouldn't be.
Like a spinning top that's getting bumped by something invisible.
And finally, we'll get to the flavor anomalies, which sounds delicious, but is actually quite perplexing for physicists.
And we'll see if this one hypothetical particle, the leptoquark, might just be the needle that threads all of these strange anomalies together into a coherent picture.
Okay, sounds like a plan, so let's structure this. We'll begin with the foundations, what we think we know. Then we'll jump into the active debate where the scientists are, currently yelling at each other in the journals.
Metaphorically yelling, of course.
Of course. Then we'll hit the frontiers. That's the leptoquarks and the incredible new machines we might need to build to find them. And finally, we'll touch on the implications. What does all this cost? And, why should we really care?
Let's do it.
All right, part 1. Foundations. Before we can really talk about breaking the standard model, we probably need to spend a minute on what it actually is. I'll be honest. I always get a little tripped up by the sheer number of particles. There are the ones we see every day, and then a whole bunch we basically never see. Can you help me visualize the hierarchy here?
Of course, to really appreciate the cracks, you have to know the building you're looking at. And broadly speaking, you can split all the fundamental particles into two big groups. You have the fermions, which are the matter particles. That's the stuff that you,
Yeah.
me, this microphone, the planet, it's what everything's made of,
The bricks.
the bricks. And then you have the bosons. The bosons are the force carriers.
Oh.
They're the mortar between the bricks. They carry the messages and the forces between all the matter particles.
Okay, let's start with the bricks there. The fermions.
So the fermions come in what we call three generations or families. And you can think of them like three sets of siblings, each one heavier and more unstable than the last.
I like that.
Generation 1 is the responsible, stable, older sibling. This is the stuff of everyday life. It's the up quark and the down quark.
Which make protons and neutrons.
Exactly. And the electron and its little ghostly partner, the electron neutrino. And that's basically the entire visible universe right there. Everything you have ever touched is made of generation 1 fermions.
Simple enough. But then it feels like nature just hit copy-paste and increased the font size.
Nature got a bit exuberant.
Yes.
Generation 2 is a heavier, more exotic copy. You have the charm quark and the strange quark, and you have the muon. Now, the muon is key to our story today. It's basically just a heavy electron.
Same charge, same properties, just heavier.
About 200 times more massive, yes.
Mm.
It's unstable, it decays very quickly, but otherwise it's the electron's big brother.
And then there's generation 3, the rock stars of the particle world.
The absolute heavyweights. You have the top quark and the bottom quark. The top quark is just a monster. It's a single subatomic particle that weighs as much as an entire atom of gold.
That's incredible.
It is. And then you have the tau lepton. The tau is the muon's even bigger, even more unstable sibling. It's almost twice as heavy as a proton.
So we have these 3 layers of matter, light, heavy, and heaviest. And the bosons, the mortar, they're the ones tying it all together.
That's right. You have the photon for electromagnetism light. You have the gluon for the strong nuclear force that holds the nucleus of an atom together. And then you have the W and Z bosons, which carry the weak force. And finally, of course, the Higgs boson, which gives all these particles their mass.
Okay. So with that cast of characters in mind, you mentioned a golden rule of the standard model, something called Lepton Flavour Universality.
Yes, or LFU for short. This is absolutely crucial for our entire discussion today. If you get this, you get why these anomalies are so important.
So this is the rule that says the universe is supposed to play fair, right?
It's the central pillar of fairness in all of particle physics. It states that the weak force, which is mediated by that W boson we mentioned, is strictly democratic. It does not care if you are an electron, a muon, or a tau.
It's flavor blind.
It's completely flavor blind. It treats all 3 of those leptons in exactly the same way. The only difference it acknowledges is their mass.
I think I remember an analogy for this from the notes, something about a train ticket.
Yes, let's use that. It's a good one.
Yeah.
Imagine the W boson is a conductor on a train. You come up to buy a ticket, and your ticket price is based on your destination. That's the type of interaction you're having.
Makes sense.
The conductor checks your ticket and charges you based on where you're going. What he does not do is look at the color of your shirt. Let's say the electron is wearing a red shirt, the muon is wearing a green shirt, and the tau is in a blue shirt.
Okay.
The conductor doesn't care. Red, green, blue, the price is the same. The strength of the interaction is identical for all of them.
So if we look at the conductor's books and we see he's consistently charging the guy in the blue shirt, a tau, a different price, and we've got a serious problem.
A massive problem,
Yeah.
a universe-shaking problem. If we ever found evidence that the conductor was charging the tau more or less than the electron, the entire standard model rulebook gets thrown out. It would mean there's a new rule we don't know about, or a new force, or maybe a new manager overseeing the whole operation. It would be a direct violation of Lepton Flavour Universality.
And that leads us perfectly into the active debate, because for the last decade or so, we have been seeing hints that maybe, just maybe, the conductor isn't being entirely fair.
That's right.
But before we get to the possibly unfair conductor, we need to talk about the train itself, or more specifically, the W boson.
This brings us to our first major case study, the W Boson Mass.
Oh boy, this one was a real roller coaster. I remember back in 2022, this was absolutely huge news. The science press was calling it the midlife crisis of the W boson. The headlines were all, physics is broken, standard model proved wrong.
It was a genuine media storm, and a scientific one too. So a little background. The W boson was discovered at CERN back in the 1980s. We've been measuring its mass for decades. And the standard model predicts its mass very, very precisely based on its quantum relationship with the top quark and the Higgs boson.
And that prediction is, what, around 80,000 something?
The number to remember is roughly 80,357 mega-electron volts, or MeV.
80,357.
Got it. For years and years, experiments at CERN in Europe and Fermilab in the U.S. measured the mass, and all the results hovered right around that number. There were some small tensions, but nothing to lose sleep over. Everyone was pretty happy.
And then, 2022.
Then, in April 2022, the CDF II collaboration dropped a bombshell.
CDF II, that was an experiment at the Tevatron Collider at Fermilab, right? That's an older machine. It's not even running anymore.
That's right. The Tevatron had already been shut down for years. But this was a small, incredibly dedicated group of physicists who were painstakingly reanalyzing their legacy data. They spent a decade trying to squeeze every last ounce of precision out of it, and they came up with a measurement of 80,433.5 MeV.
Okay, so let me get this straight. The prediction is 80,357. They measured 80,433. To a layperson, that doesn't sound like a huge difference. It's a tiny fraction of a percent.
And in almost any other field, biology or economics, you'd call that a rounding error. But in particle physics, that difference is a canyon. It was the 7 sigma deviation from the standard model prediction.
Whoa, okay, hold on. Let's put that in perspective. 5 sigma is usually the gold standard for claiming a discovery, isn't it? Like finding the Higgs was a 5 sigma result.
Correct. 5 sigma means there's about a 1 in 3.5 million chance that what you're seeing is just a random statistical fluke.
So what's 7 sigma?
7 sigma is. Well, statistically, the chance of it being a fluke is about 1 in 390 billion.
So impossible.
It's so statistically unlikely that it basically implies it cannot be chance.
Yeah.
If that number was real, the standard model was dead on arrival. It would mean the whole delicate mathematical balancing act of the universe was failing. It was screaming that there must be new, undiscovered particles, maybe extra types of Higgs bosons or supersymmetric particles that were messing with the W boson's mass.
The physics internet just exploded. I remember theorists were writing hundreds of papers overnight trying to explain it.
They were. It was a frenzy.
But here we are recording this in early 2026, and the story has changed quite a bit.
Drastically. Enter the CMS experiment at CERN. CMS of the compact muon solenoid is one of the 2 giants at the Large Hadron Collider. And on September 17th, 2024, they released their verdict.
I have the press release here. CMS experiment at CERN weighs in on the W boson mass.
It sounds like they're stepping into a doxing ring.
And what a weigh-in it was. This wasn't just another measurement. They analyzed 300 million W boson events from their 2016 run, and they ran over 4 billion simulated events to understand their detector. It was by far the most precise measurement of this value ever made at the LHC.
Okay, so the moment of truth, what was the number?
80,360.2 MeV.
80,360.2. That is...
This is almost exactly on top of the standard model prediction of 80,357. It's in perfect agreement, as they said.
So the crisis is canceled. The midlife crisis is over.
For now, it seems so, yes. The CMS result aligns perfectly with the standard model and also with the other big LHC experiment, ATLAS. The 2022 result from CDF is now the definitive outlier. It's the one that doesn't fit. Now, I want to dig into why the scientific community seems to be trusting the new CMS result over the old CDF one. It's not just because it agrees with the theory, is it?
No, absolutely not. That would be terrible science. It's about the method. You mentioned in our pre-show chat that they used a new technique.
Right, something about not using the Z boson as a reference point.
Exactly. So measuring the W mass is incredibly difficult. And the main reason is that when a W boson decays, it often produces a muon, which we can see in our detector, and a neutrino.
And neutrinos are basically invisible ghosts. They just fly right through the detector without leaving a trace.
Precisely. So you have missing energy. You don't know the full picture. The traditional way to handle this, for decades, has been to use the W's heavier cousin, the Z boson, as a standard candle to calibrate everything.
Why is the Z easier?
Because the Z boson decays into 2 visible muons. No invisible neutrino. So you see everything. It's a clean event. You can measure its mass very precisely and then use that to calibrate your whole detector's energy scale. It's like using one trusted ruler to check another less trusted ruler.
Okay, but the risk there is, if your trusted Z boson ruler is actually slightly warped for some reason, then your W boson measurement is guaranteed to be wrong.
You've hit the nail on the head.
Yeah.
It can introduce a subtle, systematic bias that you might not even be aware of. But the CMS team decided to free themselves from that historical assumption. They developed a brand new way to calibrate the detector using the geometry of the muon tracks themselves.
How does that even work?
It's incredibly clever. They mapped the detector's magnetic field and physical structure with unprecedented precision. They modeled how the metal support structures literally bend and sag under gravity, how the magnetic field fluctuates with temperature. The press release compared it to being able to measure a 4-inch pencil to within microscopic tolerances. They calibrated their energy scale without ever looking at a Z boson.
That sounds incredibly risky. I mean, if you get it wrong, you have nothing to check your work against.
It was absolutely high risk, high reward, but it paid off. By doing this, they dramatically reduced their systematic uncertainties, and it strongly suggests that the CDF II result, while performed by brilliant people with heroic effort, likely fell victim to some subtle, hidden systematic error in their old Tevatron detector that we just can't identify anymore because the machine has been torn down.
So the W boson seems to be back in line. The standard model survives its midlife crisis, but that's just one anomaly. And this next one, I feel, is even more slippery.
Oh, it is. If the W boson turned out to be a false alarm, our second case study is a genuine stalemate. It's trench warfare between experiment and theory. We have to talk about the muon G2.
The wobbling top. I love this one because the analogy is so good it involves a swarm of invisible gnats. But before we get to the gnats, can you explain what G2 even means? What is G?
Right, so G stands for the G factor. Let's go back to our muon. Imagine the muon is a tiny spinning top. Because it has an electric charge, its spin makes it act like a tiny bar magnet. We call this its magnetic moment.
Okay, a tiny spinning magnet.
Now, if you take that tiny spinning magnet and you put it in a powerful external magnetic field, it doesn't just line up, it precesses. It wobbles.
Like a spinning top or a dreidel does as it starts to slow down and wobble around.
Exactly like that. Now, according to the simplest, most basic version of quantum mechanics, an equation from Paul Dirac back in the 1920s, the value of that wobble, the G factor, should be exactly 2.
Hence the name of the experiment, G minus 2. We're looking at the tiny difference from the number 2.
We are, because we know it isn't exactly 2. And the reason is that the muon isn't spinning in a true empty vacuum, it's spinning in the quantum vacuum.
Which is not empty at all.
Not at all. The quantum vacuum is a seething, frothing soup of virtual particles that are constantly popping in and out of existence for infinitesimally short periods of time. Virtual photons, virtual quarks, virtual electrons. They all appear for a nanosecond, and then they vanish.
And these are the gnats?
These are the gnats. This swarm of virtual gnats bumps up against our spinning muon. They interact with it, and those little bumps change the wobble slightly. The anomalous magnetic moment, or GNAC2, is a measure of exactly how much the vacuum froth interacts with the muon.
So if there are particles in that vacuum that we don't know about, like particles of dark matter or leptoquarks, they would be extra invisible gnats in the swarm.
Precisely. They would bump the muon a little harder, and the wobble would be different from what our standard model calculations predict.
So the game is simple. Measure the wobble in a laboratory. Calculate the wobble on paper using the standard model. If the numbers match, we understand the universe. If they don't, there are invisible gnats we haven't discovered yet.
And that is exactly where the trouble starts. The experiment itself, which is conducted at Fermilab, is a marvel of precision. They shoot a beam of muons into a giant, perfectly circular magnetic storage ring, and they watch them wobble as they go around.
And they released updated results in 2023.
They did, and those results confirmed earlier findings from an experiment at Brookhaven National Lab. The result is unambiguous. The muon is wobbling too much. The measured experimental value is significantly higher than the main theoretical prediction we were using back in 2020.
How significant?
The tension is about 5 sigma.
5 sigma? That's discovery territory. That should be champagne corks popping, right? We found new physics.
It would be.
Yeah.
It absolutely would be, except the theorists started fighting each other. And this is what we now call the war of calculations.
Wait, how can theorists fight? Isn't math just math?
You would think so. But not when you're dealing with quantum chromodynamics, the theory of the strong force. To know if the experimental wobble is wrong, you first have to know with absolute certainty what the right wobble should be. You have to calculate the effect of that gnat swarm perfectly.
Okay.
And the hardest part of that swarm to calculate is something called the hadronic vacuum polarization. That's basically how the virtual quarks and gluons in the vacuum clump together.
Yeah.
It's messy. You can't just solve it with a pencil and paper.
So how do they do it?
There are 2 main methods, and this is the whole problem. They currently give different answers.
Oh.
Method A is the data-driven or dispersive method. This is the traditional approach, and it's what the big muon G2 theory initiative used for their official 2020 prediction. They don't just use pure math. They actually take experimental data from old electron-positron colliders to help them estimate the hadronic effects.
Oh, hold on, let me get this right. They use data from old experiments to make the theoretical prediction for the new experiment.
Yes. It's a very clever, established technique that's been used for decades. It relies on a deep mathematical relationship between how electrons can turn into hadrons and how those virtual hadrons affect the muon's wobble. And when they use this method A, there's a huge gap. Experiment does not match theory, and that implies new physics.
But then there's method B.
Then there's method B. This is called lattice QCD, and this is where you essentially try to simulate the entire universe inside a supercomputer. You create a four-dimensional grid of space-time points, you put the fundamental equations of the strong force onto that grid, and you let a supercomputer run for months to calculate the answer. No experimental data input, just pure brute force theory.
That sounds computationally insane.
It is. We are talking about exascale computing, some of the biggest machines on the planet. For years, lattice QCD just wasn't precise enough. The grid points were too far apart, the simulation was too blurry. But by 2021, a group called the BMW Collaboration, that's Budapest, Marseille, Wuppertal, published a result that had enough precision to challenge the status quo.
And what did the supercomputer say?
The supercomputer said that the hadronic gnat swarm was a bit denser than we thought. Their theoretical value for the wobble was higher than the value from method A.
How much higher?
High enough that it lands almost exactly on top of the Fermilab experimental measurement.
Wait. So let me see if I have this. If you use method A, the data-driven method, the standard model is broken and we found new physics. But if you use method B, the giant supercomputer simulation, the standard model works perfectly fine.
That is the stalemate. That is the trench war. We have an incredibly precise experiment, but we have two competing theoretical predictions, and we don't know for sure which one is correct.
And it gets even messier, doesn't it? I remember reading something about a new experiment in Russia that complicates things even more.
Yes, the CMD3 experiment. Remember how method A uses data from old electron-positron collisions?
Right.
Well, the CMD3 experiment redid those old measurements in 2023 and 2024 with a modern detector. And their new data contradicts the old data. Their new data actually agrees with the lattice QCD calculation.
So the data-driven method might have been built on a foundation of bad data all along.
It's possible. Or maybe there's some subtle effect in the different energy ranges that we don't understand yet.
Yeah.
But if CMD3 is right and the lattice calculation is right, then it would mean the standard model actually predicts the muon's wobble perfectly. There would be no anomaly, no new physics.
Another potential crisis-canceled moment.
We just aren't sure yet. The Fermilab G2 experiment is still taking data. They're going to release their final ultimate measurement. They're aiming for a mind-boggling precision of 140 parts per billion sometime in the next year or so. And in the meantime, the theory community is frantically trying to figure out why the old data and the new data disagree. But for right now, the muon G2 is a total cliffhanger. It could be the first sign of a revolution, or it could just be that we didn't know how to do the math right.
Okay. So the W boson is safe. The muon is a big maybe. That brings us to the third crack in the code. And this one feels different. This is flavor physics. This is about the B mesons.
This is where, for me, the story gets really, really interesting. And this is where that hypothetical particle, the leptoquark, really starts to look like a plausible suspect.
And we really have two anomalies to talk about here. One that died a rather public death, and another one that just refuses to die. Let's start with the one that died. Something called Rikers.
Yes. For about a decade, this was the golden child of BSM anomalies. It was the one everyone was betting on. It looked at a specific type of decay of B mesons. Those are particles that contain a heavy bottom quark. In this decay, the B meson turns into a strange quark and a pair of leptons.
And according to our train ticket rule, Lepton Flavour Universality, it should decay into a pair of electrons just as often as it decays into a pair of muons, right?
Exactly. The ratio of the two decay rates, which is what Dracos measures, should be almost exactly 1. But for years, the LHCb experiment at CERN kept seeing a ratio of about 0.85.
Meaning it was happening less often with muons.
Yes. It looked like these V mesons preferred to decay into electrons. They were discriminating against muons. This was a huge deal, a direct violation of LFU.
But there's always a but.
There's always a but.
Okay.
As they collected much more data through Run 2 of the LHC, and as they got much better at understanding their detector, Specifically, understanding how often other particles can be misidentified as electrons, which is a very tricky background, that number started to creep up. 0.85 became 0.9. And then in late 2022 and confirmed through 2024, LHCb released their final definitive analysis with all their data. The ratio is 1.0.
Consistent with unity, the standard model prediction.
The anomaly vanished. It turned out to be a combination of statistical fluctuation that didn't hold up and some very tricky experimental systematics. The standard model is right again.
Man, it feels like the standard model is just bulletproof. It just deflects every challenge we throw at it.
It almost does, except for the stubborn tau.
$20.
This is the one that I think keeps a lot of theorists up at night. This involves a different kind of B-meson decay. In this case, a B-meson decays into a charm quark, a neutrino, and a tau lepton.
The heavyweight lepton, the third generation one.
Right. And here we are comparing the rate of decay to taus versus the rate of decay to the lighter leptons, muons, or electrons. Now, taus is very heavy, so they're harder to create. The decay is naturally suppressed because energy has to be converted into all that mass. The standard model accounts for this mass difference perfectly. But even after accounting for that, multiple experiments, LHCb at CERN, the Bell II experiment in Japan, and the older Babar experiment in the US have all consistently seen too many tauses.
How significant is this deviation? Is it another 2 sigma bump that will go away?
That's the thing, it's not. The combined significance of all the experiments is somewhere between 3.2 and 4.4 sigma. It hasn't faded away with more data like Schrader did. It has persisted for over a decade across different kinds of experiments. LHCb smashes protons together. Bell II smashes electrons and positrons. They are completely different environments, and they both see the same excess.
So nature seems to have a preference for the tau, even when it shouldn't.
It appears so. The train conductor seems to be charging the tau less than the others, letting more of them onto the train. Or, to put it another way, it looks like there might be a special VIP door just for TIAS.
And that is the perfect segue into part 3, frontiers. Because if there is a VIP door, we need to have a name for the bouncer standing at that door. And that name seems to be the leptoquark.
The leptoquark. It sounds like something straight out of science fiction, but it's actually a very old idea in theoretical physics. In the standard model, as we said, quarks and leptons are totally separate families of particles. They live in different houses. They don't talk to each other directly. A quark can't just turn into a lepton.
They interact via the force carriers, the bosons, but they stay in their own lanes.
Exactly. A leptoquark would fundamentally change that. A leptoquark is a hypothetical new type of boson that would, by its very nature, couple to both a quark and a lepton at the same time. It allows them to transform into one another. It would bridge the gap. It breaks the caste system of particles.
So why does this particular idea solve the Trey anomaly? Why does it help the tau specifically?
Because if leptoquarks exist, there's no rule that says they have to interact with all the generations equally. Remember how the tau lepton and the bottom quark are both from the third heaviest generation?
Right. They're the heavyweights.
So maybe this new leptoquark particle has a special affinity for the third generation. Maybe it prefers to talk to the heavy particles.
A kind of third-generation bias.
Precisely. The technical term for one mechanism is chiral enhancement, which sounds complicated, but the basic idea is that certain types of leptoquarks can have interactions that are proportional to the mass of the particles involved. Since the tau and the bottom and top quarks are so heavy, the leptoquark interacts much more strongly with them.
So it provides an extra pathway for B-mesons to decay into tauus.
It's the VIP door. The standard model pathway through the W boson is the main gate, open to everyone. The leptoquark provides a new, exclusive side door that only TAS and other third-generation particles can use. And that neatly explains why we see an excess of tau $100. But we don't see any anomaly with the lighter electrons or muons anymore. Why towers is normal.
Okay, that's very elegant. It solves the exact problem we see. But wait, I remember from the papers something about vector versus scalar leptoquarks. What's the difference between them, and why does it matter?
This is where the plot has thickened over the last few years. So a few years ago, back when we thought both Perdora, the electron-muon anomaly, and Corida, the tau anomaly, were real, everyone was in love with a model called the vector leptoquark, specifically one named $U.
Why that one?
Because it was like a theoretical Swiss Army knife.
Oh.
With a few clever assumptions, it could explain both anomalies at the same time. It was the perfect solution.
But then the dot anomaly died.
Exactly. Chagall's went away. And suddenly, the vector leptoquark is much less attractive because it's a complicated solution to a problem that doesn't seem to exist anymore. It naturally predicts effects in electrons and muons that we now know aren't there.
So the spotlight shifts.
The spotlight shifts to the simpler models, the scalar elliptoquarks. They're named things like 702 HAR2. These are simpler particles. They have a spin of 0, like the Higgs boson. And the reason they're so exciting now, as a lot of the recent papers show, is that they are the perfect candidate for what we do see.
What makes them so perfect?
Because a single scalar leptoquark model can explain the chair letter anomaly, the tau excess, and this is the real kicker. It can also simultaneously explain the muon G2 puzzle.
Wait, I thought we just said the muon G2 was a stalemate.
It is a stalemate. But if the experiment turns out to be right, and the mainstream theory calculation is wrong, we still need a new particle to explain that extra wobble. And a scalar leptoquark can do that perfectly. It can enter the gnat swarm around the muon as a virtual particle. And because of that mass-dependent chiral enhancement effect, it could give just the right size kick to the muon's magnetic moment to explain the discrepancy.
So let me get this straight. A single new particle, the scalar leptoquark, could potentially fix the stubborn tau excess and the mysterious muon wobble all at the same time.
Exactly. It kills two major birds with one theoretical stone. And in physics, we love theories that are elegant and efficient like that. It makes it a very, very attractive idea.
Okay, theory is great. I love a good, elegant theory. But I'm a seeing is believing kind of person. How do we actually find one of these things? If they're real, where are they hiding?
Well, they have to be very heavy.
Hmm.
If they were light, we would have already produced them by the bucket load at the LHC and seen them. So we're talking about the TeV scale tera electron volts. That's thousands of times the mass of a proton. Probably somewhere in the range of 1 to maybe 50 TeV.
That's pushing the absolute limit of what the current Large Hadron Collider can do, isn't it? The LHC runs at a collision energy of about 13.6 TeV.
It is pushing the limit, yes. The direct search strategy is to look for a proton collision that produces a pair of leptoquarks, which then instantly decay into something we can see, like a top quark and a tau lepton. We've been looking for that signature for years. We haven't found it yet.
So where else do you look?
We look in what are called the high PT tails.
Okay, can you translate high PT tails for me?
Sure. So PT stands for transverse momentum. Think of it as the sideways energy in a collision. Most of the billion collisions per second at the LHC are sort of though, glancing blows. They produce a lot of low-energy junk that flies along the beam pipe. But every now and then you get a really violent head-on collision that sprays a massive amount of energy out sideways. That's high p-Dellers.
The tails of the distribution graph, the rare events.
Exactly. If heavy new particles like leptoquarks are being created virtually, they'll show up as a tiny excess of events in those very rare, very high-energy tails. We're sifting through mountains of data looking for that tiny bump.
And the LHC itself is getting a major upgrade soon to help with that sifting process, right?
Yes, the High Luminosity LHC, or HL-LHC. It's scheduled to come online in the mid-2030s. It won't increase the collision energy much, but it's going to increase the luminosity, the sheer number of collisions, by a factor of 10.
It's like turning up the brightness on our flashlight to look into the dark corners of the universe.
That's the perfect analogy.
Yeah.
We might see things hiding in the corners that were just too rare to spot with our current flashlight.
But if even the high luminosity LHC can't find them directly, we're going to need bigger guns. And this leads us to the future of the machinery and that European Strategy 2026 update.
Yes. This is a huge document. It's not just science, it's politics, economics, and it sets the roadmap for particle physics for the next half-century. And the 2026 update makes a very clear, very bold recommendation. We need a Higgs factory.
The FCC.
The Future Circular Collider, with the E standing for electron-positron. The plan is to dig a brand new tunnel at CERN. A massive, massive ring.
How big are we talking?
The current proposal is for a 91-kilometer circumference.
91 kilometers. The current LHC is 27 kilometers around. That's enormous. That tunnel would go under the Jura Mountains, under parts of Lake Geneva.
It's a civil engineering project on the scale of the pyramids. It's a monster.
Hmm.
But the idea is that this would be a precision machine. The FCCE would collide electrons and positrons with exquisite control to create millions upon millions of Higgs bosons and Z bosons in a very clean environment.
And how does that help us find leptoquarks?
It helps us find their shadows. We would measure the properties of the Higgs and Z bosons so accurately that if a leptoquark exists, even at 10 or 20 TeV, far too heavy to produce directly, its virtual effects, its quantum ripples, would cause a tiny measurable deviation in our data.
So it's like seeing the ripples on the surface of a pond without ever actually seeing the stone that was thrown in.
Exactly. And then the long-term dream, we're talking the late 21st century now, is the FCCHH. We'd use that same 91-kilometer tunnel take out the electron machine, and put in super powerful new magnets to smash protons together at 100 TeV.
And that would be a true discovery machine.
That would be a leptoquark factory. It would be capable of directly producing these heavy particles in huge numbers, if they exist.
The strategy documents also mentioned another more exotic idea, a muon collider. That sounds like the really sci-fi option.
Is the moonshot idea, yes. The problem with accelerating electrons in a circle is they radiate away energy like crazy. The problem with protons is they're messy bags of quarks and gluons. But muons. Muons are fundamental like electrons, but they're 200 times heavier, so they don't radiate nearly as much energy. A muon collider could potentially reach incredibly high energies in a much smaller ring, maybe only 10 kilometers around.
So what's the catch? If it's so great, why aren't we just building that?
Because muons die. They're fundamentally unstable. A muon at rest decays in just 2.2 microseconds.
That's not very long.
It's no time at all. You would have to create the muons, gather them, cool them down into a tight beam, accelerate them to nearly the speed of light, and smash them together, all before they simply vanish. It is one of the hardest technical challenges in all of engineering.
It's like trying to build and race a car made of ice cubes inside an oven.
That's a fantastic analogy, yes. But both the U.S. and European strategy reports are taking it very seriously. It's the high-risk, high-reward path for the future.
So we're at a real crossroads. We have these tantalizing hints of a leptoquark from the tau anomaly. We have a blueprint for these massive next-generation machines. And this leads us right into part 4. Implications, because we have to talk about the price tag.
We do. These machines, especially the FCC, are going to cost tens of billions of euros or dollars. No single country can afford it. It requires a truly global collaboration between Europe, the US, and probably Japan and China as well.
And I have to play devil's advocate here for a moment. 20 billion euros.
Yeah.
30 billion. That's a lot of hospitals. That's a huge investment in climate change mitigation. Can we really justify spending that kind of money just to measure the W boson mass to the 10th decimal place? Or to try and catch a glimpse of a leptoquark that lives for a fraction of a nanosecond?
It's an absolutely valid and essential question. And it's one that we as physicists have to answer to society. Part of the answer is about the spin-off technology we developed to find these things. New superconducting magnets, advanced computing, AI, data processing, all of that trickles down to things like MRI machines and managing the electrical grid.
Sure, the technological argument.
But I think the more important answer is about the why. You mentioned earlier this idea of the desert versus the jungle.
Right, this feels like the philosophical stake in the ground.
It is. If we choose not to build these new machines, we're making a huge gamble. If it turns out the standard model is truly all there is, and there are no new particles up to the unbelievably high energy scales where gravity kicks in, then we're facing what physicists call the desert.
No new particles, no new forces for orders and orders of magnitude of energy, just a vast, empty wasteland of known physics.
And that sounds, honestly, scientifically terrifying and a bit depressing. It would mean we might never learn the answers to dark matter or the matter-antimatter asymmetry of the universe because the energy required would be forever beyond our reach. We'd be stuck with the standard model, knowing it's incomplete but being completely unable to fix it.
The other option,
The jungle.
the jungle, is what the persistent Arderde anomaly and the promise of the leptoquark suggests. It's the possibility that just around the corner, at the TeV energy scale that these new machines would unlock, there's a rich, complex ecosystem of new particles. Leptoquarks, maybe supersymmetry, maybe new candidates for dark matter. If the tau anomaly is real, then the jungle exists.
And if the jungle exists,
Then building the FCC is absolutely worth it because we will find things that will completely revolutionize our understanding of matter, energy, space, and time.
and the leptoquarks themselves. If we find them, they imply something even bigger and more profound, don't they? This idea of a grand unified theory. They do. It's the Holy Grail. Remember, leptoquarks connect quarks and leptons. If they exist, it's a powerful hint that at some extremely high energy, back near the time of the Big Bang, quarks and leptons weren't different things at all. They were just two different faces of a single unified type of matter. It would suggest that all the forces of nature, except gravity, merge into one superforce. It brings us one giant step closer to writing down the single equation that could describe the universe in its first moments.
It connects a tiny anomaly in a particle collider today directly to the birth of the entire cosmos.
That is the magic and the beauty of particle physics. We look at the very smallest things to try and understand the very biggest things.
So to try and summarize this whole incredible story, the W boson had a scare, but it seems to be behaving itself. Crisis canceled thanks to the precision of the CMS experiment.
Check.
The muon is definitely wobbling, but we're not sure if it's the muon's fault or our math's fault. That's a stalemate for now.
A total cliffhanger, yes.
But the B-meson, specifically its strange relationship with the heavy tau lepton, is still stubbornly breaking the rules, and the leptoquark is our prime suspect for why.
And we are now in the process of designing and building the courthouse, the HL-LHC, and potentially the FCC, to finally put that suspect on trial.
It's just a fascinating time to be watching this field. It really does feel like we're standing right on the edge of the map with a little note that says, "Here be dragons."
We are. The Standard Model is the most successful scientific theory in human history. But, as the poet Leonard Cohen said, there is a crack in everything. That's how the light gets in. We're just trying to find where the light is coming from.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.